Okay, I think we're recording. Um, so today we're very happy to have Dominique Unruh, who is going to tell us about quantum UC.
Mhm. Okay, thank you very much. So for those who didn't notice it in the email, there's a whiteboard here, but you can also connect to it via a URL that was in the email. Um, this is useful if you want to scroll to somewhere where I was before, or if you want to write something on the whiteboard, which you should of course only do as part of some question that you're asking. But you don't have to because you will see the whiteboard um, here on the screen always. And it says no internet connection. I hope that's not a bad sign. So I will be talking about quantum UC. And so my talk will consist of basically two parts. The first part is telling how quantum UC is modeled. And the main message there is it's boring. I mean, if you know classical UC, then quantum UC is just the same, except you put the word quantum in the right places. And then I will proceed to develop the theory of, I mean, how you can do arbitrary multi-party computation in the quantum UC model. I mean, with classical inputs and outputs. I'm not going into computing on quantum data. And this will allow me to introduce a few interesting non-trivial things about quantum UC. And depending how much time this takes, I will also talk about everlasting security, which is a middle ground between computational and statistical security. And I mean, I have planned this quite freely. I don't have slides. I just have the board. So I'm very flexible to answering questions and to focus on things that are of interest to the audience. So let me first start by talking about quantum UC. Okay, I have to solve a little problem. The bar that has the zoom options is over the bar that has the pen selection options. Okay, I got rid of it. Perfect. So let me first recall UC. I mean, Ran already talked about this in the last two sessions, but it's useful to have the picture here. So the basic idea of UC is that you have some protocol pi, and you want to say that this protocol has all the properties of an ideal functionality rho. Now, I said ideal functionality, but in general, both of them can be protocols, but because basically all that UC does is to establish an ordering to say like pi is as secure as rho. And if rho is something ideal, then you know pi is at least as secure as this ideal thing. So pi and rho could be also two functionalities, two protocols, but the easiest case to think of is a protocol and functionality. And now how do we say that pi emulates rho or implements rho or is as secure as rho? Well, the definition says that we need to show that for any adversary that attacks the protocol pi, where attacking just means it can interact with the protocol pi over a channel that is for this particular purpose. So depending on what protocol you have, this channel could contain signals whom to corrupt, or it could, no, that has to be the environment, sorry, but it could have, for example, something like fake messages that are inserted, or it could even the adversary could impersonate another party and so on. But anything the adversary sends is just represented by this one line. And from an abstract view, this is all we need to know about how an attack works. And then what we want is that for any such adversary that attacks the real protocol, there exists a simulator that does an attack on the ideal protocol. So this simulator just needs to, it operates with a completely different protocol. Yeah, so here are some perhaps encrypted messages and so on, while here are maybe just some commands to the ideal functionality saying something like, now release the message to that participant, but the functionality never tells the adversary or simulator what this message is. And what we want is that this simulator achieves the same thing as this adversary. And so far, this is the same as in, for example, standalone security, which is known to have sequential composition, or in zero knowledge, where we have a verifier and a simulator that simulates it. So far, it's a very generic concept. The question is, what does it mean in this particular case that the simulator manages to do the same thing as the adversary? And this is done by introducing yet another party, the environment. And the environment talks to the protocol and to the adversary. So it gives inputs to the protocol and gets the outputs. And it just takes whatever information the adversary gives to the environment. And on the other hand, the same environment is also talking with the simulator and the ideal protocol, giving inputs and outputs to the ideal protocol. And what we want is that this, that was unexpected, that these two situations are indistinguishable. Indistinguishable in this case just means that the environment in the end gives an output bit, like one single bit, and and then we want that the probability of this bit being 1 is negligibly close in the two settings. So this is UC in a nutshell. And now, if we want to have quantum UC, all we need to do is to say all those machines and all those wires here are quantum. So that's basically it in a nutshell. So essentially what we have to, or maybe I draw here, like it outputs some bit B in the end, just to make this explicit. So all what we have to do if we want to go from UC to quantum UC is to define a machine model for those machines and a network model for the execution. Doing this in detail is always a bit tiresome, because you need to define all the kinds of, like, where do I put the ID of who gets it and so on. But on a high level, it's pretty simple, or on, let's say, on a level that captures the essence of what's happening. So when I want to define quantum UC, I need to have the machine model. And what I do here is just I say a machine has several registers. So I mean, there's in Rand's model, it's usually being talked about tapes of Turing machines. To a large degree, this is a matter of taste, whether you call it a tape or a register, but it is basically something where the machine, like part of the memory of the machine for a specific purpose. And the registers it has is the internal state, then a register for incoming messages, and a register for outgoing messages. And if we are just in the classical case, then these three things are just classical values, and the machine could be described as just some probabilistic function, taking the incoming, the state and the incoming register, and transforming it into a state and an outgoing register. And this outgoing register contains the message and also who should get the message and so on. And if we do the same thing in quantum, then we need to say which register is quantum, which is classical. So the state, oops, the state is a quantum state. And for the messages, at least the way I modeled it in my model, we actually split the register into two parts, a classical part and a quantum part. Although it's always possible to send classical data over a quantum channel, separating having a part of the register that is by definition classical just makes things easier. So for example, then if you say like the addresses of the recipients, they are on the classical register, then you don't need in your proofs to wonder about corner cases like what if if someone puts the address in superposition somewhere. So we have a classical incoming and a quantum incoming register, and also a classical outgoing and a quantum outgoing register. And we take the convention that the routing data, let's call it, so the information, who is the intended recipient, and or from whom does the message come, all this metadata is put in the classical part of the message, and the quantum part can contain arbitrary payload. And with this machine model, I mean, the network execution is then pretty straightforward. Whenever some machine outputs a message on the outgoing registers, you look what's written as the recipient in the outgoing classical register, and then the message is put onto the incoming registers of the recipient machine. So that's basically all there is to defining quantum UC. I should mention the environment output bit is still a classical bit, because we're just asking, can it in the end make a classical guess in which of the two games it is. Yeah. I mean, if you have any concrete questions, so if anything of this seems to you it's not kind of obvious, or when you think there might be some design choices that may matter, please just ask and I can go into that. Otherwise, I will assume that this is all that needs to be said about how to define quantum UC.
So you know, I don't know if it's a question or a thought. So something that bothered me is, you know, I talked about it maybe the first time. I don't know if you probably weren't around then, but something. So the UC model is you know, sequentializes communication, right? So every step there's only one message being sent. And you know, in the classical world, we justify it to be kind of like hand wave it, but you know, it's a good hand wave. You say, you know, this essentially captures even any concurrency, because any concurrency can be sequentialized, and you know, we just allow the adversary to sequentialize the other way it wants, so it actually captures arbitrary or whatever, potentially about the concurrency. So but in the quantum settings, I don't know. So is really this sequentialized thing enough to capture a world where messages can be sent, you know, at the same time, and messages are quantum, and maybe they're correlated? I don't know how to think about it. I didn't understand the thing enough.
Okay, it's a good question. So maybe I should add one constraint here, or I don't know, limitation or something. So it's not a limitation that has to hold in principle, but I don't know if anyone has investigated quantum UC without this limitation. So we have no superposition of different recipients, because we put the recipient in the classical outgoing part,
Right. Yeah.
and we have no superposition between sending and not sending. So you cannot just say, I, in superposition, send you the message and don't send it to you,
Right.
which could be a useful thing. I know that long ago there was some paper, but I haven't read it, but there is some analysis about trying to make a covered communique, so that you notice if someone tries to find out whether you are communicating with someone else by making superpositions of communicating and not communicating. So that could be useful, and it's not covered by this model. Maybe it's hard, maybe it's easy to extend, I don't know. But if we take this, these two limitations, if we accept that this is not something we want to cover, so we don't want protocols to do that, and then without loss of generality, I think we can say the adversary doesn't do that either, because the protocol would measure whether the message is being sent or not, and therefore you can say the adversary also doesn't do. Then the same convincing hand waving as in the classical setting also applies here, because the payload itself is data in superposition, but if you just look at the transcript, who gets a message from whom when, this is purely classical.
Right.
Yeah.
Yeah. No. So okay, good. So yeah. So, but I wonder how to think about it. Because in the world, we do basically the abstraction of communication and messages going and forth, but in the end, we're all connected right now and with fixed wires, right? Fixed physical wires, optics or whatever, and there's information sent on these wires all the time concurrently, and we just abstract it as messages being sent, not sent, or something, but down to the bottom, we are all connected all the time, and everything is happening at the same time. I don't know if it's a superposition or not, but yeah. It's much nicer to analyze things the way you do it, the way UC does it. But just a question. Yeah.
I mean, my claim, for which I don't have any formal proof or something, my claim is that this is a relevant issue, but it is orthogonal to the quantum nature of the thing. So in the same way as classically, it might be good, or it might at least make the model more realistic if you take this into account. To the same degree, this applies quantumly, but I think it's orthogonal to the quantum nature of the protocol.
Okay.
Yeah. Okay, so so now you may ask, if we do that, what changes and so on? So, I mean, first, the good news, what I call structural UC theorems still hold. Well, by structural theorems, I mean those that are not talking about concrete protocols, but that say things like the composition theorem or dummy adversary and so on. So specifically, like reflexivity, like a protocol is as secure as itself, transitivity, so if pi is as secure as rho, and rho is as secure as sigma, then pi is as secure as sigma. So that's also quite intuitive. Then also Ran, I think last time, talked about the dummy adversary, or the time before. So the fact that without loss of generality, you can assume that the adversary is just forwarding messages. This still holds. A small caveat that applies in the same way as in the classical model. This holds but it only holds if you get all the things about polynomial runtime right. I mean, so there are like very subtle differences between the models, and sometimes one of these theorems breaks down not for like actual cryptographic reasons, but just for reasons that, for example, it turns out that one polynomial time machine would have to forward messages and it can't because it runs out of runtime and so on. But if we ignore these, then the theorem still holds. And if we take them into account, then the problems are not any different from the classical ones. And the composition theorem also still holds. So any of these?
Just one quick question. I mean, is there no subtlety that comes up with the dummy adversary? Because you know, I mean, maybe it's not an issue, but like forwarding quantum messages, or if you have some entangled state with the adversary in one of the parties, that doesn't become an issue?
It has to be a quantum dummy adversary in the sense that it forwards quantum messages. But other than that, no, there's no issue. I mean, the proof is virtually, I mean, if you look at the original proof, it's at a high level, it's just about putting things into boxes and using the fact that the dummy adversary is basically nothing else as a wire split in two with a repeater in between, and then you can put two machines in one box and call them one machine and so on. All these you use only these structural properties, and all of these properties that you use still work basically the same way.
And the other thing actually that didn't come up explicitly when you defined the model, but I guess the environment has an auxiliary input, and I guess the attacker can as well. And all of that can, and the honest parties may also, you know, have some inputs, and those can all be arbitrarily entangled, right?
Well, the honest parties do not have an input per se, but they communicate to the environment.
Right. Okay.
That comes from the environment, and those are messages, and they can be quantum, and therefore they can be quantum, and therefore.
So the environment can set up the entanglement then if it wants to.
Yes. So the only party where it would make any particular where you would have any reason to add an auxiliary input, and this is also the case in the original in Rand's original UC model. So the only party where you will do that is the environment, and there you have the free choice, because also in the classical UC model. So I think I'm guessing there, Rand perhaps knows it better. I think the reason why the UC model was defined with auxiliary input as opposed to without is basically that the experience from standalone security has shown that without auxiliary input is not a good idea, because you can't show the composition theorem and so on. But with UC, it turns out you can still do it even without the auxiliary input, because the reason why you need it in the standalone model is basically to kind of capture an environment, like other protocols and so on. And this is captured by the environment directly. So composition theorem and so on, they work whether the environment has an auxiliary input or not. And in the quantum setting, you could similarly say you do it without auxiliary input, you do it with classical auxiliary input, or you do it with quantum auxiliary input. This gives you then, I mean, I would guess that that most of the security proofs will be basically the same, except that in the end you need your primitives to be secure against uniform adversaries, against non-uniform adversaries, or against adversaries with quantum advice. Yeah. Okay. But it's a matter of choice. I don't see any hard arguments for any of these variants.
Yeah, so just like you're absolutely right, Dominique. So but one other thing that is that with auxiliary input, it allows you to show the equivalence of whether there is one simulator per environment or universal simulator for all environments. Right? So with auxiliary input, it's equivalent. Otherwise, it's not.
Yeah, although that one depends, I think, very strongly on which polynomial time definition.
Right, that too. You need that too.
Yeah.
But anyway, what you want in the end is one simulator for all environment. Yeah. That's what you need for the composition theorem. Whether it's equivalent to the other one, it's a different issue. Right?
Yeah.
So for the dummy adversary, I mean, I guess for this, do I need the wire between the adversary and the protocol and the wire between the environment and the protocol to be of the same type? I mean, like, for example, like if in my setting, the adversary can only interact classically with the protocol, but the environment can interact quantumly, if I then like fold the adversary into the environment, do I now like, did I just make my problem harder? Do I now have to prove like a harder theorem?
Can you say again which wires you were talking?
Well, I mean, you know, in your picture at the top, you know, there's a wire between the adversary and the protocol, and then there's a wire between the environment and the protocol.
Yeah.
And I guess you've declared that all those wires are quantum.
Yeah.
But, okay, I mean, you know, we could also imagine applications where, let's say, the wire between A and pi is classical, but the wire between Z and pi is quantum.
Yeah. I mean, since the protocol is something that is not quantified, but you explicitly say what it is. So if you say it's a classical protocol, or if you say it's a protocol that sends only classical messages over the network or something like this, or to the adversary, this way you would make this wire effectively classical. I mean, the model doesn't enforce it, but they can become classical. And in that case, a classical dummy adversary would easily be shown to be also sufficient. While if there can be quantum messages on this channel, then of course you need to make the adversary also able to read quantum messages. And the third option, to say the wire between the adversary and the environment is classical, but quantum between the protocol and the adversary, then you get an incomparable model, and then the dummy adversary would not hold anymore. So it would be a very interesting model, because now you would say there's a quantum attack, but I still need to convince the environment with only classical information that I did an attack. So unclear what this means. And then all bets are off for the structural properties. I would have to go through them again. I mean, the dummy adversary clearly doesn't hold them. With the others, I would guess they hold, but I would have to look carefully to be sure.
So, yeah, it's not clear to me that the model, you know, what is the rationale. But you're talking about the model where all the communication says quantum, except for the communication between the adversary and the environment.
Exactly.
Yeah, it's not clear. Yeah, what this means.
Yeah.
Yeah. No, but the point is, I don't know. So what I understood from your answer, which I agree with, just to make sure that I understood correctly, is that the communicate. It could be the case where the communication between the environment and the protocol, direct communication between the environment and the protocol, which kind of like models the inputs and the outputs of the protocol, is classical.
Yes.
But the communication between the protocol and the adversary / simulator is quantum.
Yes.
One example. Yeah.
One example is quantum key distribution, where you create a classical key, but on the network there is quantum communication.
Right.
Yeah.
And the dummy adversary should work there. So the dummy adversary theorem should work there too.
Yeah, but it has to forward quantum data to the environment then.
Yeah. Okay.
Mm-hmm. Okay, so let me see where I was. Yeah. So this basically captures like the analogy of classical UC in the quantum setting. And as I said, the message is nothing bad happens. Of course, if you prove a concrete protocol, like if you have a concrete protocol and you ask, is this quantum secure? Then it depends very much on the protocol, whether this protocol suddenly becomes difficult to prove, because you need to consider quantum things. But so all I'm saying is that quantum UC holds no surprises on the structural level. On the level of concrete protocols, sometimes it does, sometimes it doesn't. So I mean, I've encountered both. And in order to kind of give an overview of that, I want to talk about multi-party computation. So let's say we want to implement a multi-party computation functionality. Well, quantum UC multi-party computation. So we want to implement a multi-party computation functionality. I don't want to write down an explicit definition of this functionality because we will actually not look at that particular functionality anyway. It's just some functionality that takes outputs from people, does some computation, and gives outputs, and basically the all the inputs are classical, all the outputs are classical, but the protocol that implements this might use quantum communication. So okay, maybe I should draw it anyway. So the functionality FMPC has classical input from all parties, then does some computation, output is f of input, and gives then classical output to everyone involved. I mean, I'm ignoring things like corruption and so on. The reason why I do that is that anyway, I will only use existing classical results. So the only results that actually talk about this functionality will be classical results that I can lift as in a black box way to the quantum setting. So the overall plan, how we will do this is we want to realize MPC, and we do this in the very traditional way of saying we realize an OT functionality. We also realize a secure message transmission, so a secure channel. So with a secure channel and with OT, we can implement, at least in the classical world, this goes already back to Kilian 81, we can implement multi-party computation. But in the quantum setting, we go a bit farther. I should say that I want this information theoretically secure. So this is already long known in the standalone model. It is also reasonably long known, I mean, 12 years in the UC model. But what we can in the quantum UC model, we can add some more arrows. We can say, well, obvious transfer, instead of taking it as a black box, we use commitment as a building block and try to implement the OT functionality using commitments. And similarly, so I will come to that in more detail, and similarly, the secure message transmission or secure channel, we take an authenticated channel and implement from this secure message transmission. So this upper part is something unique to the quantum setting, because we know that we cannot get information theoretical secure channels from authenticated channels, and we cannot get information theoretically secure from commitments. So there's the big difference between quantum and classical. So,
Dominique, are you talking about passive or malicious MPC or
malicious? Yeah,
malicious. Okay.
Yeah, everything I'm saying is malicious.
Right. So would it be easier for honest but curious, or it doesn't matter?
Honest but curious is almost undefinable in the quantum setting, because honest but curious says that you are looking at the messages, but you're not changing them.
I see.
And
I see.
Yeah, so there have been some attempts to have definitions that somehow capture some of these properties, but they are more like there's, for example, specious adversaries, but they are not really capturing any realistic attack model. They're more like technical definitions as stepping stones in a multi-layer construction. Yeah.
I see. So you're saying not even just go, you don't even need to talk about the communications. Also, when you look at the states of corrupted parties and stuff, the internal states, also you can do it. But I guess the one thing that I'm just thinking out loud, is one interpretation of passive security or unspecified is after the fact, right? So so the thing happened, and after the fact, you look at the transcripts of the communication and some of the internals of the parties.
Exactly, and in the quantum setting, there is no such concept as the transcript of the communication either. I mean, you can have a transcript of all the classical data that is sent, but you cannot make a transcript of the quantum data because that you would need to copy it.
I see.
And since any adversary could just choose to put all the messages that are sent, well, it could just choose to artificially keep everything in the quantum state and never use the classical state, then the transcript will only just contain who got what message. I mean, who
right.
I mean, the metadata. Yeah.
Okay. Thanks. Okay. Interesting.
And this also has an effect on on one structural property of UC, because in classical UC, you have two equivalent definitions. You can say we have the output bit of the environment, and that needs to be indistinguishable. Or you could say the view of the environment has to be indistinguishable. And those are quite easily seen to be equivalent. But in the quantum setting, you cannot do that because there is no such thing as a well-defined view of the environment, because the view contains the transcript of all messages. Okay, so first, as a look ahead, so what are the things, the ingredients?
I was muted. I said thank you. Yeah.
So for this one, we will use quantum key distribution. For this one, we will use a protocol that is based on a very old protocol by Bennett, Brassard, Crépeau, and Saiwine. So this is, in the non-UC setting, a well-known fact that you can get an OT from commitments in the quantum setting. And this protocol here, it goes back to Kilian. But for the UC setting, it was Ishai, Prabhakaran, Sahai in 08 who showed it for classical UC, and we just need to see how we deal with it in the quantum setting. So I will start with this part. So here, some more scrolling. Oops. So the first step in this picture is how to get from OT to multi-party computation. And Ishai, Prabhakaran, Sahai, they showed that there is a protocol that takes an OT and implements an arbitrary multi-party computation functionality in classical statistical UC. Just as a reminder for those not familiar with it, statistical UC is UC where the adversary, the simulator, and the environment can be unlimited. So we don't require them to be computational, but we have the one additional constraint that if the simulator is polynomial time, so is the adversary. No, the other way around. If the adversary is polynomial time, so is the simulator. This is an important. Without this condition, you would have that statistical UC does not imply computational UC, and that would be a bit paradoxical. So this is a known result. I have no clue how this result is proven, and I want to use it as a completely black box. And now your first idea might be to say, well, in the statistical case, all these things like quantum computers and so on, they don't matter because we are talking about unlimited anyway. So shouldn't this just imply quantum statistical UC? The answer will be yes, but let me first tell you why this is something we should not take for granted. Because like in the standalone model, for example, so the one that doesn't have an environment that interacts with the protocol and adversary life, we do not know whether classical statistical security implies quantum statistical security. As far as I know, we don't have any counterexamples, but we also don't know that it holds. And even for much simpler settings, for example, one special case of the standalone security model is zero-knowledge proofs. Zero-knowledge proofs are just standalone protocols for a very particular functionality, namely the functionality that checks the prover's input and tells the verifier whether it's correct. So if we ask, like, if we have classical statistical zero knowledge, we don't know whether the same protocol is also secure as a quantum statistical zero knowledge protocol. Okay, the order of letters is usually different, but anyway. So,
so by the way, Dominique, when you say the first one, you know, classical statistical that imply quantum, I guess you're talking about, you will be talking about polynomial time, because you know there is this Grover thing, right? You can speed up by square root, by a factor of.
But I'm talking about statistical security,
like a random function inversion or something like that.
Yeah, but I'm talking about statistical security, so the runtime doesn't matter anyway.
Oh, but I guess but yeah, runtime in terms of right as opposed to queries. Okay.
And I'm talking about a classical protocol because it doesn't make even sense to talk about classical security of a quantum protocol. So if we have a completely classical protocol, we could ask, is it still secure in the quantum setting? So can quantum adversaries do something bad to an already statistically secure protocol? Okay. And the best example for something seemingly completely trivial, where we don't know, is the graph isomorphism zero knowledge protocol, the standard well-known one where you pick get an isomorphism between one graph or another. So that protocol is statistical zero knowledge. It's even perfect zero knowledge in the classical setting, and we don't know whether it's zero knowledge at all. No, wait, we know whether it's zero knowledge. We don't know if it's a proof of knowledge. Right. So we know it's a proof of knowledge classically. We don't know if it's a proof of knowledge quantumly. And this is about completely statistical. It's about statistical security. Yet we only know these things for very special cases. So this shows that we should not take for granted that a classical protocol with a classical proof is secure in the quantum setting. However, in the UC case, it turns out that everything works fine. So this is, and it's surprisingly simple. So I will show you now what I call the quantum lifting theorem. Because it allows us to lift a protocol from the classical setting into the quantum setting. And it says if pi is classical statistical UC emulates rho, then the same thing holds in the quantum setting. And it also implies the quantum computational UC emulation because that's weaker than statistical. So this theorem, if we have this theorem, we have solved the first thing in our picture here, namely getting multi-party computation from secure message transmission on OT, because we just take the existing protocol from IPS, and we know that it is also quantum statistical secure. So let me give you the proof, because I can really go through the whole proof in 6 little pictures. It's just a tiny bit harder than the dummy adversary theorem. So the situation we have is we have an adversary, an environment, or well, kind of many because it's for all, and the protocol, and they interact. And what we want to show is that this is indistinguishable from a situation where some simulator, which we don't know yet how to construct it, but we want to put something here so that these two pictures are indistinguishable from the point of view of the environment. That's our goal. The protocol here is classical, pi and rho by assumption, because otherwise we can't even talk about classical UC. But the adversary may not be classical, the environment may not be classical, the simulator may not be classical. So what I will do to keep things like a bit more explicit is I will, oops, wrong button. I draw an orange circle always about everything that's classical, just to keep it straight in our mind, what's classical and what not. So the first thing that we can do is we take the same protocol, the same network, but we insert a repeater here. So a machine that takes the messages coming from the protocol and forwards them to the adversary and vice versa. So in this sense, it's similar to the dummy adversary. Yeah, it's completely dumb. It just forwards messages between adversary and protocol. Now, since the protocol pi is quantum, there will classical. There will be only classical messages here, and therefore we can also assume that the repeater is classical, because well, the adversary might send quantum messages, but those would be measured anyway by the protocol, so the recipient can also measure them. And we have that the view of the environment is identical in these two settings because we just inserted a repeater. And now we can draw a box, around these two, meaning that we construct one machine that just simulates those two. And this machine here internally is quantum, but the communication is purely classical. So we can replace this by a classical exponential time simulation of this combination of two machines. Oops. Oh, sorry. Talking to R and pi. And now everything we have here, oops, that's not very pretty, well, but all those machines are now classical. And now we are in the setting of classical statistical UC. Here we need statistical because this machine runs exponential time, even if those were not, because this machine simulates a quantum computer. But now we have some machine here interacting with the protocol and R. So we can say R is now the adversary, and this machine is now the new environment. And then the fact that we do have classical statistical security means we have that this is indistinguishable from the same environment so exactly the same machine, talking to the protocol rho and to some simulator S0. All of them classical. So this is how we made use of the classical protocol, by just showing that we can, without loss of generality, treat a lot of things as classical. Now we can take this. I mean, this was just a simulator for this, so we can unwrap this, and this is equivalent to A talking to Z, talking to S0, talking to rho, with now, only these things being classical. That should have been, wait, that should have been S0, and that should have been a rho. And the final step is to say these two machines together here we just define to be our simulator that we want in the end. So this is the same, whoops, as this network which we wanted. So now we know that this is equivalent to this. So as you see, we can, by purely kind of structural reasoning, show that statistical security implies, classical security implies quantum security. And if we are in the computational setting, it doesn't fully work because we introduce this machine that is a classical, an exponential time machine, but we can get an analogous theorem that says if we have classical UC with respect to machines that are internally, that can run a quantum computer internally, but outside, like all communication is classical, which would be some kind of post-quantum crypto UC, like the adversary has a quantum computer, but everything that happens outside is classical. The same theorem also works, which is something that came up in the last seminar.
So Dominic,
yeah.
So this setting that you just mentioned now seems maybe actually in some ways maybe a little better than the than the one that's on the board.
Yeah.
I guess if there's auxiliary information, I mean, I know you said earlier that maybe we don't have to worry about auxiliary information, but I guess if there's auxiliary quantum information that the environment gets, then I'm not sure how you would do this classical exponential time simulation.
Well, the auxiliary input is then is quantified then with the environment. So in the unlimited setting, you could just say the environment is, I mean, you don't, well, auxiliary input could take even more than exponential time to compute, but we are actually, this exponential is, I just put whatever class it happened to be in, but the model does not require this to even be computational. So it could be a machine with a description of the auxiliary input state hard-coded.
And there are no settings where you would potentially need to worry about auxiliary information, which is sort of outside the environment and provided kind of once, and that's kind of it. And the environment doesn't know or can't access, you know, how this state was prepared.
I don't think so, because the environment is the only party that gets it, and therefore the environment. You could also say that the environment just tries all possible auxiliary inputs. I mean, with quantum states, you need to discretize, but you could. But if you're exponential time anyway, or doubly exponential, you can do it and just make a simulation first. Which of these is the best for distinguishing, or any of these tricks? So I'm not. So at least the theorem works, even if there's auxiliary input. I don't know if there are like variations of UC where what you raise might be an issue. I mean, there are various variants of UC which one could investigate also in the quantum setting, but none comes to mind.
And I guess in this setting that you just mentioned, where A and Z can internally, where everything's polynomial time, and you can and A and Z can internally simulate arbitrary quantum algorithms, then there, I guess it's not an issue at all, because they could just take the auxiliary state as input. And
yeah, I mean, then you would need to
then there's no
make
problem.
your kind of post-quantum UC model in a way that this auxiliary input is just still there.
Right.
Yeah. But the fact, I think the classical variant, the computational variant of this is probably less useful, because I find this theorem particularly useful for reusing existing results where you didn't have to care about quantum nature at all. While in this, I'm not sure this post-quantum UC, as I just called it, is actually simpler to handle in the proofs, because you still need to think about the quantum nature of the environment and so on. Or even if you say it's classical, completely classical machines in a runtime class that is equivalent to quantum computers, you still run into the same problem. So I was a bit excited once when I discovered this originally, but I have never since run on any use case of this theorem in the computational case, while the statistical one I think is definitely useful. So now there is the time question, because we have reached the end of the hour. I mean, I'm flexible, but I guess that a lot of you have also other commitments and so on. So the question is, I mean, I guess this was interesting information on its own. I mean, there is no necessity to add other things, but I have also a lot of other things to tell. So what should I do? I mean, what's the interest?
So I'm free for the next 25 minutes, but I'm also happy, to continue next week. I mean, we don't have any time constraint and time limit on those meetings, right? So I don't know what people prefer.
I mean, if Dominique, if you feel like you have another meeting's worth of content, maybe we can continue next week.
I think I can fill one more meeting, and that will round it up off nicely.
Okay, that sounds good.
Yeah. Okay, then we will do that next week, and I think it's a good point for stop. I mean, I will answer any questions for this content so far, but I won't add new content today, and next week I will continue.
I just want to say first, thank you very much. It was great. But regarding Gordon's question, what you say, so it sounds to me, without actually writing down the proof, but like what I said last time is that so in the computational setting, outside the statistical case that you described, I think what you get is that if you have a classical result, then you have kind of a generic way to transform it to a quantum result. In the following sense, you could just leave the simulation the same. Usually the result, a proof of security is, first you have to write the protocol, second you have to write the simulator, then you have to show that, the two environment cannot tell the difference. So you don't have to rewrite the simulator. The only thing you have to rewrite is the proof that the environment cannot tell the difference, because now you have to reduce it to a quantum safe assumption. And if you could do that, then you're great. And maybe you can't, then you have to redo the whole thing from scratch.
Exactly. Yeah. And in many cases, I believe you can do that. So it's a good rule of thumb to say, if you already have a computation with classical result, don't try to use this generic theorem. Just use the same simulator and try to prove the indistinguishability again. And I think it often works. But one case that I had was, for example, what I'm going to be able to cover next week, at least a bit. It was one protocol, everlasting security, where there it turned out that the classical it just didn't work, and I had to even change the protocol completely because because in the subproof sometimes you need additional steps. I mean, sometimes I mean, UC doesn't allow you to rewind, but sometimes in a UC proof, while showing that the simulator actually works, you need to prove that certain messages or certain events cannot hold. And for that, you use zero knowledge, and for that, you use rewinding and so on. So it could be that that proof actually completely fails because you use purely classical techniques on the way when showing your simulator.
Can I ask a quick question? Maybe, I don't know if you were planning on covering this next week or not, but with regard to the FCOM functionality in the quantum UC model, do we know how to achieve this with a CRS, or what's known about realizing that?
I mean, I'm assuming in this picture, FCOM.
Yeah, no, in the picture, you're treating it as an ideal.
Yeah, but I mean, I'm talking just to avoid ambiguities. This is a commitment functionality with classical message that is put in. So it's a classical functionality, and we want to implement it with a quantum protocol. And if your goal is computational security, then you just take the same protocols that worked classically and try to reprove them. Of course, I mean, if the classical protocol is based on RSA, it will not work. I mean, there is no general theorem, but it does work with a lot of the protocols. But if you, yeah, but next week I will talk about something going beyond that, because it's kind of a pity, because in this picture that I have here, everything is information theoretical. So you may ask yourself, and then if I implement the commitment from a CIS, I've lost that all again. And then I could have just stayed, I mean, then I haven't gained anything. So next time I will talk about how we can get something that is not achievable in the classical setting, namely everlasting security, not from a CIS, but still in a way that is impossible classically. So the classical things still work as long as you pay attention to your post-quantum crypto, but you may get even better things quantumly.
Okay. Good, well, thanks.
Yeah.
Thanks. I'll stop the recording now.